Alright, let's go. Number 10. The information paradox. In the early 1970s, Stephen Hawking wasn't trying to break physics. He was trying to reconcile two theories that already worked, general relativity and quantum mechanics, by asking a simple question: what happens to a black hole over very, very long timescales? Quantum mechanics has one unbreakable law: information cannot be destroyed. Whatever falls into a system, whatever happens to it, the universe keeps a perfect record. Erase the record, and you erase the rulebook. Hawking found that black holes emit radiation and slowly evaporate. Eventually, they disappear completely. And whatever fell in, every atom, every photon, every scrap of information about you, if you fell in, evaporates with it, into radiation that carries no trace of what it once was. Hawking published this result in 1976 in Physical Review D in a paper titled Breakdown of Predictability in Gravitational Collapse. He didn't hedge. He stated plainly that quantum mechanics, as understood, would be violated. Physicists tried everything. Some argued the information leaks out encoded in subtle correlations within the radiation, but no one could show how. Some proposed the information survives in a Planck-sized remnant, but remnants that small couldn't hold that much data without violating other laws. Leonard Susskind spent years developing black hole complementarity specifically to patch this hole. And even he later admitted the fix created new contradictions. Hawking himself conceded a partial defeat in 2004, buying John Preskill a baseball encyclopedia to settle a losing bet. If the information is gone, then somewhere in the universe's deep future, there will be radiation with no history behind it. Your entire life, if it ever crossed an event horizon, would not survive as a memory anywhere. Not encoded, not hidden. Erased from a universe that isn't supposed to allow erasing. 50 years later, no one agrees on where the information goes, only that it has to go somewhere. The math said the record should survive. The horizon said otherwise. Number 9. The Firewall. In 2012, 4 physicists at UC Santa Barbara, Ahmed Almheri, Donald Merolf, Joseph Polchinski, and James Sully were trying to patch the information paradox using Suskind's complementarity idea. They weren't hunting for a new problem. They were trying to close an old one. General relativity makes a specific promise. An observer falling through a black hole's event horizon should feel nothing unusual at the moment of crossing. No wall. No violence. Just empty space, until the crushing tide of the singularity much later. Almheri's team found that promise couldn't survive alongside quantum mechanics. To preserve information without duplicating it, the event horizon couldn't stay smooth. It had to become a wall of extremely high-energy quanta, a firewall, that would incinerate anything crossing it instantly. Their paper, Black Holes, Complementarity, or Firewalls, was published in the Journal of High-Energy Physics in 2013. Known in the field as AMPS, it forced a choice: give up smooth spacetime at the horizon, or give up one of the founding principles of quantum theory. Every proposed fix failed to satisfy everyone. Susskind and Maldacena proposed ER/EPR, wormholes connecting entangled particles, to avoid the firewall, but it introduced its own unresolved geometry. Stephen Hawking proposed in 2014 that event horizons don't exist in the strict sense at all, only apparent horizons, a suggestion most physicists found too radical to adopt outright. No consensus was reached. None exists today. If you fell into a black hole, current physics genuinely cannot tell you which death you'd experience. The gentle stretching predicted by Einstein, or instant combustion at the boundary predicted by AMPS. 2 of our most trusted theories disagree about the exact texture of your final moment. Which one is it? Nobody can say, and both cannot be true. Neither theory blinked. That's the part nobody expected. Number 8. The Ringdown Echoes. In September 2015, LIGO detected gravitational waves from 2 merging black holes for the first time in human history. The collaboration wasn't hunting for anomalies in the aftermath. They were confirming Einstein's century-old prediction even existed. General relativity predicts that after two black holes merge, the resulting object rings briefly, like a struck bell, then settles into silence as the signal decays smoothly and disappears. That decay pattern, the ringdown, is one of gravity's most precise fingerprints. In 2016, physicists Vitor Cardoso, Edgardo Franzin, and Paolo Pani, working from Lisbon and Rome, proposed something stranger. Faint repeating echoes arriving after the main ringdown, delayed pulses that shouldn't exist if the event horizon behaves as classical relativity demands. Their paper, Is the Gravitational Wave Ringdown a Probe of the Event Horizon?, appeared in Physical Review Letters in 2016. They reanalyzed the original LIGO data and reported tentative echo signals at roughly the level statisticians call weak but present, around a 1 in a few hundred chance of being random noise. The LIGO collaboration itself pushed back hard, arguing the echoes were consistent with detector noise. Independent teams split down the middle. Some found echoes in the same data. Others found nothing when they reran the analysis with different assumptions. No fraud, no error, just two teams staring at identical numbers and reaching opposite conclusions. If echoes are real, it means the event horizon isn't the clean, one-way boundary general relativity describes. Something at the edge is reflecting information back out, ever so slightly, into space-time we can measure. Meaning the darkest objects in the universe might not be fully sealed after all. The data hasn't ruled it out. It hasn't ruled it in, either. Number 7. The ER_PR Conjecture. In 2013, Juan Maldacena and Leonard Susskind weren't trying to unify two mysteries. They were separately staring at two of the strangest results in 20th century physics and noticed the math kept overlapping. Standard quantum theory treats entanglement, two particles instantly correlated regardless of distance, as fundamentally separate from wormholes, the hypothetical tunnels through space-time predicted by general relativity. Different phenomena, different equations, different physics departments. Maldacena and Susskind proposed they might be the same object described two different ways. Entangle two particles, and you may have built a microscopic wormhole connecting them, non-traversable and invisible, but geometrically real. Their paper, Cool Horizons for Entangled Black Holes, was published in Fortschritt der Physik in 2013. The shorthand, ER_PR, fused Einstein-Rosen bridges with Einstein-Podolsky-Rosen entanglement, two 1935 papers by the same physicist, quietly describing one thing all along. Critics pointed out the wormholes required are non-traversable, meaning nothing can pass through, so the conjecture explains nothing an experimenter could ever confirm directly. Others noted it only works cleanly for maximally entangled pairs, not the messy partial entanglement found in real quantum systems. No experiment has verified it. None currently can. If true, it means every entangled particle pair in every physics lab on Earth is quietly linked by space-time geometry, a microscopic bridge nobody can see, cross, or measure directly, meaning space itself might be woven out of entanglement, with geometry as the side effect and correlation as the cause. We may be able to entangle particles daily and never once touch the bridges we're building. Number 6. The Holographic Principle. In 1993, physicist Gerard de Hooft wasn't trying to reinvent reality. He was trying to solve the information paradox by counting how much information a black hole could physically hold. Ordinary intuition says a three-dimensional object's information capacity should scale with its volume, more space, more room for data. That's how every computer, every book, every brain works. Ed Hooft found black hole entropy doesn't scale with volume at all. It scales with the surface area of the event horizon, a strictly two-dimensional quantity. His paper, Dimensional Reduction in Quantum Gravity, circulated in 1993. Leonard Susskind formalized the idea in The World as a Hologram, published in the Journal of Mathematical Physics in 1995, proposing that all information within any volume of space can be fully described by data encoded on that volume's boundary. Physicists tried to contain the implication to black holes alone. It didn't stay contained. Juan Maldasena's 1997 ADS-CFT correspondence extended the principle into a fully worked mathematical duality between a bulk universe and its boundary theory, cited more than 20,000 times since, and never successfully restricted back to black hole physics only. If the principle applies to the universe at large and not just black holes, then everything you've ever touched, including your own body, may be a projection of information stored on some distant boundary of space-time, the 3 dimensions you live in downstream of 2. Nobody has found the edge that boundary is supposed to be printed on. Number 5. The Singularity Theorems. In 1965, Roger Penrose wasn't trying to prove reality breaks down. He was trying to determine whether the collapsing stars predicted by Einstein's equations were mathematical artifacts or physically inevitable. General relativity, taken seriously, predicts gravitational collapse compresses matter into a point of theoretically infinite density and 0 volume, a singularity, where the curvature of spacetime becomes undefined. Penrose proved, using topology rather than approximation, that under broad and realistic conditions, collapse into a singularity isn't an exotic edge case. It's unavoidable. His paper, Gravitational Collapse in Space-Time Singularities, appeared in Physical Review Letters in 1965. Stephen Hawking extended the proof in a 1970 paper with Penrose in Proceedings of the Royal Society. Showing the same logic that predicts black hole singularities also predicts one at the origin of the universe itself. Every attempted fix failed on its own terms. Quantum gravity was proposed to smooth the point away, but no complete theory of quantum gravity currently exists to confirm it. Loop quantum cosmology proposed a bounce replacing the singularity, but produces predictions not yet tested against any observation. String theory offers competing pictures depending on which version is used. General relativity is the theory that correctly predicts orbits, timekeeping in your phone's GPS, and the bending of starlight. And that same theory, applied honestly to its own equations, predicts a point where it stops making sense, including, if Hawking and Penrose are right, at the very beginning of time. The theory that describes reality also describes exactly where it can no longer describe reality. Number 4. The Hawking radiation entropy problem. In 1993, physicist Don Page, a former student of Hawking's, wasn't disputing that black holes evaporate. He was trying to track precisely how the information inside should behave as that evaporation unfolds. If information is preserved, as quantum mechanics demands, the entropy of the emitted radiation should rise, then fall back down as the black hole shrinks, tracing a curve that returns to 0 once evaporation completes. Page found Hawking's original 1975 calculation didn't produce that curve. It predicted entropy rising in a straight line for the black hole's entire life, then dropping instantly and impossibly to 0 at the final moment. A jump with no physical mechanism behind it. Page published Information in Black Hole Radiation in Physical Review Letters in 1993, describing the smooth curve information theory actually requires, now called the Page curve. For over 2 decades, no calculation from first principles reproduced it. String theorists tried using ADS-CF dualities and got partial matches under simplified conditions only. Loop quantum gravity approaches produced their own curves that didn't fully agree with Page's. It wasn't until 2019, using techniques involving quantum extremal surfaces, that separate teams finally derived something resembling the Page curve directly from semi-classical gravity, decades after Page first showed the books didn't balance. The gap between Hawking's original math and reality sat unresolved for over 40 years, inside the single most cited black hole calculation in physics. If the entropy accounting was wrong for that long in the field's founding result, the question isn't whether other assumptions are broken. It's how many. Number 3. Black hole complementarity. In 1993, Leonard Susskind, Laris Thorlacius, and John Uglum weren't trying to invent a paradox about perspective. They were trying to save the information paradox from a different contradiction. The no-cloning theorem, which forbids a perfect copy of quantum information from existing in 2 places at once. If information is both destroyed inside the horizon and preserved in the outgoing radiation, that looks like cloning. Forbidden, on paper, without exception. Susskind's team proposed both could be true, depending entirely on who's asking. To an observer falling in, information falls through the horizon normally. To an observer watching from outside, that same information appears smeared and radiated away at the horizon, never crossing it at all. Both descriptions are complete. Neither observer can compare notes, because the falling observer can't send a signal back out. Their paper, The Stretched Horizon and Black Hole Complementarity, was published in Physical Review D in 1993. It didn't resolve the paradox so much as relocate it, a rule stating no single observer can ever catch the contradiction in the act, by design. The AMP's Firewall paper in 2013 directly attacked this framework, arguing complementarity itself breaks down under certain conditions unless the smooth horizon is sacrificed. Susskind spent years afterward defending revised versions of his own proposal against his own field. If complementarity is correct, reality genuinely depends on which side of the horizon you're standing on, not as a metaphor, but as two mutually exclusive, simultaneously true accounts of the same falling object, neither one ever provably wrong. Two true stories about the same event, and no observer alive to check them both. Number 2. Interior time reversal. In 1963, mathematician Roy Kerr wasn't trying to unsettle the concept of time. He was trying to find an exact solution to Einstein's field equations for a black hole that rotates, something the original 1916 Schwarzschild solution, built for a non-rotating object, couldn't describe. Outside any black hole, space and time behave as expected. You move freely through the 3 dimensions of space, and time moves you forward. One direction, no choice involved. Kerr found that inside a rotating black hole's inner region, the roles swap. What was a spatial direction becomes something you're pulled through inevitably, the way you're normally pulled through time. And time itself becomes a direction you could, in principle, move through like space, backward, forward, sideways. Kerr published gravitational field of a spinning mass as an example of algebraically special metrics in Physical Review letters in 1963. The solution is exact, not approximate, and describes almost every real black hole in the universe, since nearly all measured black holes rotate. Physicists have debated for 60 years whether this interior region survives contact with real, imperfect, infalling matter, or gets destroyed by instability before anything could experience it. Roger Penrose himself proposed the strong cosmic censorship conjecture specifically to argue this region shouldn't be physically accessible. And numerical work since has produced conflicting verdicts depending on the exact type of black hole modeled. If the region is real and reachable, then somewhere inside nearly every black hole in the observable universe, the equations that govern your own forward march through time simply stop applying, replaced by a direction that behaves like space instead. Kerr found the exact solution in 1963. Physicists still don't agree on whether nature ever lets you reach it. Number 1. Rotating black hole time loops. In 1968, physicist Brandon Carter wasn't trying to build a time machine. He was trying to fully map the geometry of Kerr's rotating solution, tracing out every region the equations described, including the ones nobody had bothered to chart yet. Standard causality assumes time only moves forward along any physical path you could travel. This is treated as close to inviolable as physics allows, the backbone of cause coming before effect. Carter found that deep inside a rotating black hole, in the region near what's called the ring singularity, the Kerr metric mathematically permits closed time-like curves. Paths through spacetime that loop back on themselves, returning a traveler to their own past. Carter published Global Structure of the Kerr Family of Gravitational Fields in Physical Review in 1968, laying out the causal structure in full mathematical detail. Kip Thorne, decades later at Caltech, took the results seriously enough to study wormhole-based time travel formally. Concluding the physics couldn't rule it out on paper, only on grounds of practical instability. Every proposed safeguard has been incomplete. Instabilities at the inner horizon, described by Eric Poisson and Werner Israel in a 1990 paper in Physical Review D, suggest infalling matter would trigger a runaway curvature spike that seals off the loop before anything could pass through it. But this has been proven for simplified, idealized cases only, not for every real black hole under every real condition. If the loops survive intact anywhere in the universe, the equations governing your own timeline permit, in principle, a path back to a moment already lived, not metaphorically, not as science fiction, but as a solution Einstein's own theory does not forbid. 60 years later, no one has proven the loops are impossible. Only that reaching one might kill you first. 10 anomalies. 10 separate teams, separate decades, separate corners of physics. None of them were hunting for a crack in reality. They were doing ordinary work, counting radiation, mapping metrics, closing old arguments, and the crack found them instead. Notice what's missing from this list. Fringe theories, disproven ideas. Physics abandoned at the margins. Every single entry sits inside general relativity and quantum mechanics, the two most rigorously tested frameworks human beings have ever built. The universe isn't confused about what happens at a black hole's edge. We are, and the theories keep insisting, calmly, precisely, that our confusion is the accurate description. If you want to see more videos like this, click the video on screen now.